And what are the various properties of these graphs will also be discussed, and present these graphs, because graph is a fundamental concept in mathematics and will be used in design and analysis of algorithms, data structures, and so many other applications. So we will be talking about the fundamental details of the graphs first, explaining about the various concepts behind it. And coming to the representation, because we have to store the graph in the memory in a particular form, so that can be accessed, processed for a specific application wherever the graph data structure is really useful. So we have three methods like adjacency matrix, adjacency list, and adjacency multi-list. Now these are the three ways of representing a given graph. Of course, we have not yet defined what exactly a graph is, but I assume that you might have already studied in the mathematics. So having that knowledge, we can easily say that it could be represented in one of these three ways, and each one has its own merits and demerits. For instance, when we try to talk about graphs, we always talk about vertices and edges. So a set of vertices and edges may be called as a graph. So it's a data structure. Fundamentally, it's a non-linear data structure actually, and you can get cycles. You have varieties of graphs, and in order to represent, in order to store these graphs, different types of graphs, we may use one of these three methods or ways by which we can represent. And we will also take a lot of examples in order to show these graphs and how exactly they look like in memory and how do we actually access them. Now, once we represent these graphs or understand the basic concepts of graphs, we can actually go for the traversal methods, because for any particular application which uses these graphs, now we need to know that how do we traverse the graph, because graph has cycles, unlike your tree or tree data structure or arrays or any other data structure for that matter, which are basically linear. For example, linked list, you can traverse the linked list very easily starting from the first node to the last node, because last node will have a node without any next address, so it will be null. Similarly, tree, of course, you have studied already three ways of traversing, like in order, pre-order, and post-order. So that's again, you know, the ways by which we can start from a particular node and visit each and every node and try to use this information in each node for some specific purpose. So we need to traverse. It's mandatory that we need to traverse, because not just to store the information in some form like a graph, but we need to actually go through these nodes, and in the graph, of course, we should ensure that we don't keep on, visiting each and every vertex again and again, because graph data structure has got the cycles. So that's where the problem comes. So we have systematic way of traversing these graphs using DFS and BFS, popularly known as depth first search and breadth first search. Now, these are the two ways by which we can start from a particular vertex and then visit each and every vertex without revisiting, of course. Also, we encounter what is known as connected components, because of the varieties of the graph, different types of graphs, we may have to get some subgraphs kind of thing, where each one could be called as a connected component. In fact, in computer graphics, these image processing, so these connected components play a very major role, and we have algorithms to find the connected component. So we will study about what exactly the meaning of connected component and how do we actually get this from a given graph. Now, spanning tree is another important concept. In fact, we study minimum spanning tree. You will probably study in 4th semester of how to find minimum spanning tree. There are two popular algorithms called as Prim's and Kruskal's. But here we don't go into finding the minimum spanning tree, but we simply study about what exactly a spanning tree means. How do we actually find from a given graph? And lastly, we have what is known as bi-connected components. So this is cut vertices. They normally call it, several authors. So we have to have some fundamental concepts in order to find the bi-connected component. So we have some add-on concepts need to be introduced. So that will be the last topic, and probably if time permits, I'll also add a lot of applications where the graph will be used as the main data structure. In fact, in 4th semester, you will study a very popular problem called as traveling salesperson problem, or TSP, traveling salesperson problem. That's one of the very popular problem which is solved using are representing it first of all using graphs and then adopting several methods, maybe brute force or branch and bound, etc. So there are several methods which we can apply in order to solve. So graph is a very important data structure which people need to study in order to solve several problems on Earth. Okay, now we shall move on to the basic definition of graphs. So it was introduced by Euler graph, in 1730s. This was the first paper which talked about graph theory and all about the graphs. In fact, it was a popular paper written by Euler called as 7 Bridges of Königsberg. In fact, the problem still exists. You can Google it and find the solution also, how to find it. It's a fundamental common sense kind of thing. Well, so this is represented as a graph. You can see in graph theory. Right, so what is a graph? Graph is fundamentally defined as a set of vertices and edges. So it's a set. You can see it's enclosed within flower bracket. So V is nothing but vertices and E is nothing but edges. So any graph we normally call this as of vertices. You can see here in this figure A. Now you have 5 such vertices. So we have 1, 2, 3, 4 and 5. All these vertices in some way are connected using some edges. These are the edges, for example, between 1 and 5. So normally an edge is represented with a set of vertices, like 1 and 2 you have an edge. So this edge is connected between 1 and 2, 1 and 3, or 1 and 3 there is no edge, sorry, 2 and 3. So it doesn't mean that every pair of vertices should be connected with edges. It's not mandatory, but we have different types of graphs, maybe connected, disconnected, directed, all that. So this is called as undirected graph because each edge does not have any kind of direction. That means it's something like two-way. If you make an analogy of the graph, like in TSP, as I mentioned earlier, I may call that each vertex may represent a city and edges may represent roads. So it is nothing but that the entire city and road map or no road can be shown as a graph. So because cities are connected by roads, so like vertices are connected by the edges. So some of the roads could be two-way, that means I can travel from 1 to 2, or I can travel from 2 to 1. Similarly, I can travel from 2 to 3 and 3 to 2. Remember, an edge is normally connected between two vertices. So don't get confused with the traveling mechanism where I could travel from, for instance, 2 to 5. Via 1 I can reach 5, via 3 and 4 I can reach 5, or I can go to 1, go to 4 and then reach 5. So there are several paths, several routes, something like Google Map. So you have several paths because of these edges. See, since I don't have a road or an edge from 2 to 4, so I cannot go to 4 directly, but I need to take a different path via some edges like 2 to 1, 1 to 4, or 2 to 3, 3 to 4, etc. So since it is undirected, I can either travel from 2 to 1 or 1 to 2. So we say that there exists a path between 1 and 2. There is no particular direction which is mentioned here. On the other hand, supposing if we look at this figure B, where I have each edge being shown with an arrow like 1 to 2. So I cannot go directly from 2 to 1. I could probably go from 2 to 1 via some other edges. Sorry, yeah, it just means vertices. But 1 to 2 is a direct edge, so I can travel or I can go, move, send packets. So computer network, for example, another example where we have vertices representing computers and edges representing the connectivity in terms of wired or otherwise wireless. Doesn't matter. But traveling from 1 to 2 is possible because of this directed edge. Similarly, if I consider 3 and 4, I can travel from 3 to 4 as well as from 4 to 3 because I have edge from 3 to 4 as well as 4 to 3. So this is called as directed because I have some direction or directed edges being shown between any two vertices. Well, so these are two major types of graphs which we talk about, that is undirected and directed graphs. Rest. So these are some of the applications which people use it in several fields, like in electrical engineering, where we talk about electrical network. So I may have switches, I may have connecting boxes where power, I mean the current or the electricity, electrical network. So we have electronic network also. We have so many components connected by copper lines on the wires. So, it establishes a sort of network. So network graph we use interchangeably. So we have vertices representing these electrical switches, points, and wires indicating the edges. So there is a definite connectivity in terms of the wired connection. Telecommunication engineering, I may have connectivity in terms of the broadband, as I tell, maybe internet, via we have some communication components like routers or bridges, gates, all that. So the gateway we talk about. So there are a lot of communication components involved which are formulated in terms of a communication network and establishes that. And computer network, yes, in the field of computers, you may have a TV network also, you may have mobile network. So these are all very popular kind of networks, but only thing is that some of these networks may not be visible as such, like in normal road kind of physical kind of thing, because these may be like not wired. For example, mobile network, it's not wired, but still you have connectivity. Okay, so we have these are the vertices, mobile phones, and the connectivity via mobile network, we establish connection. So we say that from mobile 1, so there is a connectivity. People can talk from mobile 1 to mobile 2 or mobile 2 to mobile 1. It's a two-way communication. Okay, so computer network, we have local area network, we have wide area network and things like metropolitan area network. So we have LAN, MAN, WAN, different types of networks are there, which actually establishes as wired or wireless kind of thing. But essentially, the overall the structure remains same, where we have set of vertices and set of edges. Similarly, we can show a road map, which as we have already seen, that the cities indicate the vertices and the roads indicate the edges. There's another very popular problem like TSP, as I said, coloring of the map. That means you have a map with so many cities, and no two cities, neighboring cities, should have the same color. So you should ensure that whatever be the neighboring cities, you should ensure that the color should be different. And finding the shortest path, like in Google Map, we give the source and the destination, and Google Map gives you all possible paths, shortest paths actually, starting from your location or some source location to the destination. For example, assume I want to travel from Bangalore to Chennai, so it might show me all possible shortest paths. So it's so easy day-to-day life, even within the city or outside the city. So traveling purposes, we use this quite quite often in order to find the shortest path. Now this again, the road map is represented or modeled in terms of a graph. So graph of applications, and interestingly, we have the basic ones here to be studied. Right, so we have what is known as directed graph, as we have already shown in the earlier slides. Each edge may be shown in terms of a directed edge. Undirected, there is no specific direction. You can go from any vertex to another vertex, like 1 to 2 or 2 to 1, if we are talking about that undirected graph. Okay, so we have two very important terminologies used: in degree and out degree. So what is in degree? In the case of a directed graph, is the number of edges which have, say, like V as their terminal vertex. That means how many vertices actually incident on a particular vertex. That means the number of edges. For example, if the in degree of 2, for example, you have 1 and 2. 2 edges are incident on this vertex 2. On the other hand, if you take 1, there is no edge which is incident on 1. Actually, both are outgoing. So incoming and outgoing. So similarly, out degree is nothing but for any vertex V, the number of edges which have V as the initial value. That is how many edges are going out. So we can have, for instance, 1 has got 2 edges going out. So the out degree of 1 is 2. Similarly, the in degree of 2 is actually 2. In degree of 1 is 0. So no edge is incident on this one. So it's a very simple concept. In degree means how many edges incident on any vertex. Out means how many edges are going out from any given vertex. So this in degree and out degree is given normally for a particular vertex. Okay. This is another very important one, which is normally shown both for directed as well as undirected graph. So the concept of connectivity is different, or it differs between the directed and undirected graph. So we shall take undirected graph first. So undirected graph, as the example, if you are given, so we can actually show two ways by which the connectivity issue is mentioned. For instance, this figure which is shown in A is called as connected. Why? Because there exists a path between every pair of vertices. There exists a path. Remember, direct connectivity is different from a path. This is direct connectivity. 1 to 2 is a direct connectivity. Whereas 1 to 5, there is no direct edge. Direct connectivity is not there, but I can get a path to reach 5 via several other vertices. For example, 1 to 2, 2 to 4, 4 to 5. So I can actually get a path to go from 1 to 5 via 2 and 4. That means, so I should take every pair of vertices. So I'll start with 1. Okay, so 1 to 2, yes. 1 to 3, yes. 1 to 4, yes. 1 to 5, yes, I can travel. Similarly, take 2. 2 to all the rest of the vertices. So 2 to 1 I can travel, 2 to 3 I can travel, 2 to 4 I can travel, 2 to 5 I can travel via this. The next you take 3. So 3 to 1 I can travel, 3 to 2 I can travel, 3 to 4 there is no direct, but I can travel like this. 3 to 5 same way, like this. I'll just delete, erase this. So 3 to 5 I can go like this. So next take 4. For 4 to all the vertices, other vertices, 4 to 1, 2, 3, 5. Similarly 5, 1, 2, 3, 4 I can travel. So essentially this graph is connected simply because of the fact that there exists a path between every pair of vertices. On the other hand, if it fails, that if I cannot travel or I cannot get a path for every pair of vertices, then it's called as disconnected graph. For example, this is a graph of 6 vertices. Don't think that they are isolated kind of thing. It is not it is a graph. So the number of vertices, because it is in compliance with the definition. It's a set of vertices and edges. So I have 6 vertices and for 5 edges. You can see here 1, 2, 3, 4, 5 edges. That's it. But I cannot travel from 1 to 5 because I don't have connectivity. 2 to 6 I cannot travel, so it fails. So we can call this as a disconnected graph. It's called as a disconnected graph. So the word disconnected is normally used for undirected graphs rather than for directed graphs. So now let's move on to, for directed graphs, we use what is known as strongly connected. So what do you mean by strongly connected and weakly connected? We can call that way also. And some people, will talk about mixed graph, both directed as well as undirected edges, because some roads may be two-way, some roads may be one-way. So if I want to represent both one-way and two-way, probably I need to go for a mixed graph, but let's not worry about that. We talk about either undirected or directed straight away. So for every pair of vertices, there exists a path from I to J and a path from J to I. If so, it is called as strongly connected. Strongly connected concept is applicable only for directed graphs. Okay, so if I can travel from I to J as well as from J to I, it is called as strongly connected. For example, this graph, 1 to 2 I can travel, 1 to 3 I can, like this, like this. Then 1 to 4 again like this. 1 to 5 again like this. So actually if you go through, you can travel from any vertex to any other vertex. So that's what it ultimately means. That's why it's strongly connected. Now here it may not show as a separate entity like this, 5 and 6 separate. But if I cannot travel from I to J and J to I, for example, from I, let's say 1, I cannot travel to 2. So this may be I'll just select the pen. Yeah, so this may be I and this may be J. See, J to I can travel, 2 to 1 I can travel, but I to J I cannot travel because there is no way, like there is no outgoing edge from I. Now supposing if I have something like this, and let's take another edge, something like this. In case I'm just talking about I and J only. So I can travel from I to 3, that means 1 to 3, and 3 to 2, that means I to j is possible. But unfortunately, that is not there for the given graph. If this is I and this is j, I can travel only from j to I and not from I to j. So as per the definition, though it's not isolated, still it is not strongly connected. Maybe you can say weakly connected, or in this case, it may be called as disconnected. So the definition of connectivity varies from undirected to directed graph. Another possibility is called as weighted graphs. Now, so far, all these graphs, we have not attached any weight to the vertex. So it's all assumed as one unit. See, the weights, what we represent here, or write the number between 1 and 2 may represent or may signify, it may be a cost of traveling in the road map, for instance, or is the distance in kilometers or miles, or it could be the fuel consumed, time taken. So there are so many things. The Google map might give you both distance wise what is the shortest path, or it might give you the time, you know, whether traffic is something like that, traffic conditions, or traffic status, real time traffic. So all these are possible if we attach some kind of a weight to each edge. So that's called as weighted graph. So when I say this graph undirected with some weights attached to the edges, like 8 is the cost or unit, 8 units is the value attached between 1 and 2, and 1 and 4, 3 and 4, 4, 2 and 3, or 3 to 2. So that means traveling from 2 to 3 and 3 to 2, it is same, the cost is same. On the other hand, if we have the directed graph, then we have same thing, but the cost of traveling from, for instance, 4 to 2 may differ from 2 to 4. But here, cost of traveling from 2 to 3 and 3 to 2 like 20. 4 and 4 to 2, or any pair of vertices, if the cost is different, suppose if the cost is different, then it signifies that the cost of traveling from I to j and j to I may not be the same. So we have to be very careful about the weighted network, whether we are talking about directed or we're talking about the undirected graph. No? So the weighted graph means that we have some weight, some value, some number which is attached to each edge. On the other hand, if it is not attached, I mean, if you don't attach anything to the edges, we can consider that it is one unit. That's it. Okay. Okay, now we will go for graph representations. Now, how do we actually represent the graph? Because remember, this is a graphical one. Like we have so many vertices, we have so many edges, fine. But can we store this graph in memory? See, our memory is a linear one. Like I have the address which you already studied. You know, I may have the address of this memory is 1000. I have some value. See, 11 is the value. And I may have another address in memory called 2000. Then it may be called as that I have, say, 330 may be my value, or I may have a string being stored in some memory location. So these are the addresses and this is the value which is shown linearly. So it is the memory which contains some data. That's it. So this data is available starting from this memory location to this memory location, finished. But what I have here is a data structure where I have some vertices, I have some edge details, I have some weight details, I have so much of details for each and every graph. So how do I store this graph in memory? Then only I can actually access. So that's where the concept of adjacency matrix, adjacency list, adjacency multi-list comes into picture. So what is adjacency matrix? So we are going to map the graph. You see, this is a real world graph into a electronic form or the matrix form so that we can access this algorithmically or using program. So basically adjacency matrix is a square matrix with n rows and n columns. With n rows and n columns. Because I have so many vertices and so many. See, remember that we need to represent both the vertices and also the connectivity issue. That means edge details. So whether there exists an edge between 1 and 2 or not. So that's why it's called adjacency matrix. For example, these are the vertices adjacent to a particular given vertex. For example, if I take undirected, which is simple. So if I take 1, which are the vertices adjacent to 1? It is 2 and 4. 3 is not adjacent to 1. Okay, there is no direct edge, but there is an edge, there is an edge. So 2 and 4 are my adjacent vertices, or there exists edges. So that's exactly what we call as an adjacency matrix. So we try to store this using n rows and n columns, where n is the number of vertices. So what do we store in this matrix? The contents. Okay, the entry in each matrix depends upon, for undirected graph, a 1 or a 0. So remember, adjacency matrix is a Boolean matrix. So the contents will be either 1 or 0. So what does 1 mean? When do we put 1? When there is a direct edge. That means if I comma j belongs to the edge list. If I comma j belongs to the edge list, or j comma I belongs to the edge list. Now it is mentioned as 0. Supposing if we don't have a direct edge, either I to j or j to direct edge. It's very important. See, it doesn't mean that you can travel from 1 to 3 via 2. So I can put 1 between 1 and 3. No, I should have a direct edge. Okay, I should have a direct edge. So I to j directly. Right, so we'll show how I can represent the given graph in adjacency matrix form in the next slide. Now, same thing here for the digraph or the directed graph. The matrix A, each entry I comma j will be 1 if there exists I to j, because j to I is represented using another edge. So any j, for example, I to j 1 to 2, I can put a 1, but not 2 to 1 because there is no edge. Whereas 2 to 4, I can put 1 for both 2 to 4 as well as 4 to 2. Right. So we have now a digraph or a directed graph where, if at all we mention, the adjacency matrix for digraph, then we need to follow this. It's almost that we have to be very careful about the directed edges. So now we'll take an example in order to see how adjacency matrix can be written. Okay, so this is the first example where this is an undirected graph. So I have 5 vertices. So it's a 5 by 5 matrix. You can see number of columns is 5 and number of rows is also 5. So let's now examine the first row. Okay, now from first row, that means 1 to 2. These are the adjacent vertices 1 to 3 and 1 to 4. So 1 to 2 I should put 1. You can see here 1 to 2 is 1. Now 1 to 3 is 1. Then 1 to 4 is also 1. Now you can see 1 to 5 is 0 and 1 to 1, this is not a loop. There is nothing like this. So we can say that the first row consists of 3 edges, actually 1 to 2, 1 to 3, 1 to 4. Similarly, let's take 2, vertex 2. Now from 2, I have, now I'll just pick some other color. Yeah, so now I have 2 to 1, I have 2 to 3, or let us now delete everything. Okay, now 2 to 1, 2 to 3, 2 to 4. So you can see here 2 to 1, 2 to 3, 2 to 4, marked as 1 and the rest as 0. Now let's take the next vertex, which is 3. So you have 3 to 1, 3 to 2, that's it. So 3 to 1, 3 to 2, 1, and the rest are 0. Similarly, let's take fourth vertex, that is fourth row. I'll just erase this. Now 4. Now I have 1, 2, and 5. So for 1, 2, and 5. So from 5, I have only one connectivity is 4, 5 to 4 is 1. So I have now the adjacency matrix where if there exists a direct edge from any vertex to any other vertex, I just have to put it as 1, otherwise put it as 0. Okay, now directed one, same thing, 1 to 2, I have 1 to 2 only. Only one edge is there, so only one will be there. And from 2, I have 2 to 3 and 2 to 4. From 2, 2 to 3 and 2 to 4. That's it. Okay. So we will stop here and then start again in the next lecture, because this is the way by which we can represent as adjacency matrix and adjacency list. Adjacency multi-list, of course, we can just discuss with again examples. Thanks for watching. We will meet soon.